So we're going to explore here again the derivatives of the inverse trig functions. We have a theorem that says that the derivatives of inverse functions, if f is differentiable at every point on an interval I, and the derivative of f is never 0 on I, then f has an inverse, and f inverse is differentiable at every point on the interval f of I. So as long as our function isn't equal to 0, and then its inverse is going to be differentiable as well. So we're going to look at our trig functions, and we're going to use some implicit differentiation to find the derivative of the inverse trig function. So remember, arcsine and inverse sine, these notations mean the same thing. So don't be confused if you see one or the other, they're interchangeable. So if we take the sine of both sides, then we get the sine of y on the left, and the sine of the inverse sine is going to be just x. Now, we can then do implicit differentiation on sine y equals x. So the derivative of sine is going to be cosine of y, and then times the derivative of that inside function y prime, and on the other side, the derivative of x is 1. So from there, solving for y prime, we get 1 over the cosine of y. Now we have to go think about what this means. So we're going to draw our reference triangle here, and here is our angle theta. And since we are talking about an inverse sine, an arc sine of x, that's an angle. So remember, an arc sine or an inverse sine is an angle whose sine is x. So that means that the opposite side of that angle theta is x, the hypotenuse is 1, and from Pythagorean theorem, we can get that this adjacent side is going to be the square root of 1 minus x squared. So what we're saying here is that our derivative is going to be 1 over the cosine of y. And we can see from our picture in SOHCAHTOA, the cosine of y is adjacent over the hypotenuse. That's going to be the square root of 1 minus x squared. So what we're saying is that the derivative of arcsine of x is 1 over the square root of 1 minus x squared. Okay, we're going to repeat this kind of maneuver, this strategy for a while, and when we get to some of the later ones, it's going to get a little more complicated and we'll have to talk. But let's see if we can figure out how to do our arc cosine of x in the same manner. So again, we're going to this time take the cosine of both sides and get cosine of y is going to be equal to x. We'll do implicit differentiation and get negative sine of y times y prime is equal to 1. We'll solve for the y prime and get a negative 1 over the sine of y. We'll again go to our reference triangle. This time we want the angle whose cosine is x. That's going to make the adjacent x and the hypotenuse 1, and the opposite side the square root of 1 minus x squared. So that means we're going to get our y prime is going to be negative 1 over, and the sine of y is going to again give us that square root of 1 minus x squared. So in following the same kind of pattern that we have seen earlier with the derivatives of the trig functions, we're seeing that that also holds for the derivative of the inverse trig functions, that if we can remember one of them, then we get the derivative of its cofunction, inverse cofunction, will just be the negative of that. Okay, so then we can move to our arctangent. So y is going to be an arctangent of x, and again we'll take the tangent of both sides and get tangent of y is equal to x. We'll do our implicit differentiation and get secant squared y times y prime is equal to 1. Solving for the y prime is going to get us to 1 over secant squared y. And in this one, we can, let me make sure I'm doing what I want. Yep, so we can draw our triangle here, and we can see that the angle whose tangent is x means we want opposite over adjacent to be x. That's going to make our hypotenuse, using Pythagorean theorem, the square root of 1 plus x squared. So we have, since secant squared is the reciprocal of cosine squared, what we're really getting here is our cosine squared, and that should be y's, cosine squared y. So what we get here is that cosine is going to be the adjacent over the hypotenuse, and we're going to square it, and so what we're going to get is no radical, but just 1 over 1 plus x squared. So the derivative of our tangent of x is going to be 1 over 1 plus x squared. I'm going to go on to the next panel, see if you can figure out what you think the derivative of arc cotangent will be. So I'm going to see if we can do this one without actually working it out, if I can get my pen back. So the derivative of arc cotangent of x is, and you can do this one if you need to see it, it's going to be negative 1 over 1 plus x squared. Now the derivative of arc secant gets a little dicier. Now it starts to get a little more challenging. Let's see if we can work our way around this. So we're going to start as we did before and take the secant of y is equal to x, and taking the derivative we'll get a secant y tangent y, y prime is equal to 1. So we will again solve for y prime and get y prime is 1 over secant y tangent y. So let's draw our reference triangle, and we started with an inverse secant of x, so that's an angle whose secant is x. So cosine is adjacent over hypotenuse, so secant is going to be hypotenuse over adjacent. And when we do that, we're going to get, for this side, the square root of x squared minus 1. Notice the sign is a little different order than it was earlier with the inverse sine and the inverse cosine. So it would appear anyway that y prime is going to be 1 over, and the secant of y is going to be, since the cosine is adjacent over hypotenuse, the secant will be hypotenuse over adjacent. It's going to be x. The tangent is opposite over adjacent is going to be square root of x squared minus 1. Now it turns out, and we can show this in class, but it turns out that we can show that when you look at the graph of y equals secant of x, when you look at that graph, secant inverse of x, you will see that it is always increasing. So it's what we would have called a monotonic function, a strictly monotonic function. But because it's always increasing, that means its derivative has to always be positive. And so what we have here with that x is it will be positive when x is positive, but negative when x is negative. And so what we have to do instead is insert an absolute value there to guarantee that that derivative will always be positive. So the derivative of, and I'm going to call it an arc secant, but it's the same as an inverse secant. So the derivative of an arc secant of x is going to be 1 over the absolute value of x times the square root of x squared minus 1. In a similar fashion, if we have an arc cosecant of x, then its derivative is, so let me write it as the derivative of arc cosecant of x is going to be a negative. It has to always be negative because it's always going to be decreasing. So to guarantee that it's always negative, we're going to go negative over that absolute value and the square root of x squared minus 1. So to summarize, let's see if we can write these down real quick. The derivatives of our inverse trig functions. So in summary, we know the derivative of arc sine of x is 1 over the square root of 1 minus x squared, and the derivative of arc cosine of x is then negative 1 over the square root of 1 minus x squared. The derivative of arc tangent of x is going to be 1 over 1 plus x squared. Notice it's the one that doesn't have any radical at all. The derivative of arc cotangent of x then is negative 1 over 1 plus x squared. The derivative of arc secant of x is 1 over absolute value of x times the square root of x squared minus 1. And the derivative of arc cosecant of x is negative 1 over the absolute value of x times the square root of x squared minus 1. It's worth noting that, as you look at these, that since the radical is always non-negative, that our arc sine is always going to be positive, our arc cosine is always going to be negative. And again, since x squared is always positive, 1 plus x squared is always positive, so the derivative of arc tangent is always positive, and the derivative of arc cotangent is always negative. And we talked about how the derivative of an arc secant is always positive, and the derivative of an arc cosecant is always negative. Let's go to a new panel, and we'll do a couple of examples here. So let's find the derivative of, say, arc secant of, whoops, lost my pen, 3x squared. So we're going to take, now the derivative, and we haven't really talked about the chain rule, but let's make sure we refresh our memory. So the derivative of arc secant of u is going to be du over the absolute value of u and then times the square root of u squared minus 1. So our du is going to be 6x. We'll have the absolute value of 3x squared, and then we will have the square root of u squared is going to be 9x to the fourth minus 1. So the calculus is done. Now, if we think really hard about how we can simplify this, we have to be a little careful. Now, an x squared is always positive, so we don't really need that absolute value. So we're free to drop that absolute value. Now, once that absolute value is not there, now we can look to try to cancel, but we have to be a little bit careful with the variable part there. So the way the original is that because the denominator is always negative, always positive rather, then the sign of this will depend on the sign of that value x. When it's positive, our derivative will be positive, and when it's negative, our derivative is negative. We just have to make sure that after we do our canceling that we have preserved that. So we're free to cancel the 3's. There's no consequence there. We can cancel this x with one of those, and then we just stop and think that when x is positive, this resulting derivative will be positive. That's consistent with where we started. And that when this x is negative, our original derivative would have been negative also. So we're okay with that cancellation. And we're going to end up then with 2 over x square root of 9x to the fourth minus 1. Okay? Let's do, is there another good one? So I think we'll stop right here, and I think I'll make a new video for just the derivative of an inverse function in general.